Okay, first we will think of principle of superposition. So for example, I'm taking two waves with the displacement y1 equivalent to a1 into sine of omega t minus kx and y2 equivalent to a2 into sine omega t minus kx2. So first we will find out the phase difference between the two waves. So then the phase difference. So already we know this total value is called as phase. So when we take the phase difference delta phi, so equivalent to phase 2 minus phase 1, that is omega t minus kx2 minus of omega t minus kx. So finally we get k into x1 minus x2. So this will be the final wave. So when we think of the principle of superposition, so the resultant wave can be expressed as y equivalent to y1 plus y2. So when we take that wave as y equivalent y1 plus y2, we will get y equivalent to a sine omega t minus kx plus 5 we will get. Already we have calculated the 5 phase difference. Uh, so we need to think of the amplitude. So we have an amplitude principle A equivalent to root over A1 square plus A2 square plus 2A1 A2 cos phi. A1 square plus A2 square plus 2A1 A2 cos phi we get. So this will be the amplitude. For example, I am taking this will be A1 and we are taking another wave. This will be A2. So this will be A1 and this will be A2. So then we are taking the resultant. So we are taking the resultant as this. So this will be A. So let us take the resultant makes an angle phi. So that phi can be estimated from the formula tan phi is equivalent to, this is very similar to the vectors resultant. Tan phi equal to, when we think of these vector as p and this is q and this is 2pq cos theta, like this we have a formula in vectors. So p square plus q square plus 2pq cos theta. And also we have tan alpha is equivalent to q sin theta by p plus q cos theta. So similar to that, so we are taking this A1 as P and the A2 as Q. Similarly, we are taking this formula tan alpha is equivalent to, or tan phi is equivalent to A2 sin phi by A1 plus A2 cos. So in this way, we will estimate the resultant wave and as well as phase shift. Next, we have been focusing on another application. For example, we are taking y1 equivalent to a1 into sine of omega 1t plus kx1 omega 1t plus kx and y2 equivalent to a2 into sine of omega 2t plus kx2. Now the phase difference we will understand. So we know the phase. Phase means the total angle is generally called as phase. So when we take the phase difference, we will write omega 2 minus omega 1 into t plus k into x2 minus x1. Suppose if the y1 and y2 are the waves which are generated from coherent sources. So already we know according to wave optics, coherent sources means their frequencies are same, wavelengths of lights are same, or the angular frequencies also same. So in such a case, the phase difference becomes we will get k into x2 minus. k into x2 minus x1. So this will be the discussion. This will be the discussion. And according to the relation I equivalent to 2 pi square a square f square rho v. So intensity is found to be amplitude square. So we know the resultant principle also. So the resultant I equivalent to, generally we have an expression I1 plus I2 plus 2 into root of I1 I2 cos square. So this is the resultant intensity whenever the two waves superpose with each other. So whenever the two waves superpose with each other, so this will be the resultant wave. So this is about the resultant wave. So just I will take a problem regarding the phase difference. For example, we have two light sources or two sound sources like S1 and S2. So which are separated by a distance some 3 units. A point P is located here. The point P is located here. So its coordinates, the point P coordinates are given as, so let us say 2, 4, 2, 4 we are having. And S1 is at the origin, S1 is at the origin, and S2 is at a distance 3, 0. So in such a case, first we will understand the thing. So you're measuring, suppose if you take this is the y-axis and as well as this is the x-axis. Y component means distance from x-axis. This is x-axis. So this distance will be 4. And x component means distance from y-axis. So automatically this distance will be 2. This distance will be 2. So in that case, so automatically this becomes, so according to Pythagoras theorem, we are having 4 square plus 2 square. 16 plus 4, 20. Okay. So therefore we are writing S1P equivalent to root 20. So nearly it becomes 4.8. And also we are taking S2P. This is 1. So automatically according to the Pythagoras theorem, again we will get a 4 square plus 1 square. So we are going to get 4.1. So the equivalent to 4.1. Suppose if the question is given like this. So at the P, when two sound waves are emitted from S1, S2, at the P, if we have maximum sound, so whenever we have maximum sound, automatically we will take the path difference. The path difference delta x is equivalent to 4.8 minus 4.1. 4.8 minus 4.1 means that is equivalent to 0.7. So that is path difference when we have the maximum sound. So whenever we have a path difference of at least lambda, we have the maximum sound. So that is the condition. So therefore we are taking lambda equivalent to 0.7. For example, in the question, if the velocity is given as 350 meter per second, so then we can estimate the frequency. So V equivalent to F into lambda or F equivalent to V by lambda. So that equivalent to 340 by 0.7. So it is meter per second. So this is an important model. So regarding the path difference and as well as phase difference. So now we need to understand the most important and difficult topic. So that is reflection and as well as transmission, reflection and transmission of waves, reflection and transmission of waves. Reflection and transmission of waves. So we are taking its properties. So we are taking the properties which changes. So generally, in the case of reflection, what happens to the nature of that property? And let us see, in the case of transmission, what happened to the property? So we will discuss right now. So to understand properly, we are taking a tabular form. To understand it properly, we are taking the required the discussion. Okay. So first, before discussing this, we need to understand what we mean by reflection and transmission. For example, if a wave is incident on a surface, some part is again reflected back to the same medium. So this is called as reflection. So this is called as reflection. And if some part of the medium, some part of the wave will be shifted to the second medium or into another medium. So this is called as transmission. Transmission. So here we will discuss each and every parameter, the nature. So this is very important for the case of wave optics and as well as here waves, velocity. So velocity. So this velocity is purely depends upon medium. So this velocity you need to understand it purely depends on medium. So in the case of reflection, it will back to the same medium. Same medium. So కాబట్టి ఇక్కడ ఏం రాసుకోవచ్చు అంటే the velocity remains the same. In the case of transmission, the medium changes. So automatically the velocity changes. So in this way, we will understand the discussion here. Next, we think of frequency, angular frequency, and time period. So this is very important. In the case of reflection or transmission, so that means even though the wave is traveling in the same medium or if the medium also changes, in the case of reflection and transmission, so everything remains the same. The frequency remains the same, angular frequency remains the same, and time period also remains the same. So next, we are focusing on wavelength lambda. Wavelength lambda. Wavelength lambda, or else we will take and k, wave propagation constant, k equivalent to 2 pi by lambda. So we will call k as wave propagation constant. Wave propagation constant. So you need to understand one thing. When we take v equivalent to f into lambda, so if the velocity constant, wavelength also constant. As it is given velocity is same, so automatically the wavelength is also same. Because the wave will be back in the same medium. The wave will be back in the same medium. And after that, in the case of transmission, we are taking in the case of transmission, it will changes because the velocity changes, it will changes. So next, after that, so we used to think of phase difference. So in the case of reflection, we have two conditions. The phi value equivalent to 0 when the reflection takes place at a rarer end. So rarer end. And it suffers a phase difference pi equal to pi when the reflection takes place at the denser end. So we will discuss it later. What do you mean by rarer end? What do you mean by denser? In the case of transmission, there is no phase difference. There is no phase difference. So in this way, we need to understand about the basic properties. So we are taking first reflection at free end. Reflection at free end. So reflection at free end means, so we used to call this as rarer at rarer end. Free end, or we used to call rarer end. So let us understand what do you mean by reflection at rarer end. For example, we have a rope. We have a rope. We have a thick rope. We have a thick rope. And in addition to this, we have a thin rope, very thin rope. So this is thin, and obviously this is thick. Suppose if we understand a wave, and that wave is reflected back again. If that wave is reflected back again, at the boundary of thick and thin. So this is called as reflection at free end or reflection at rarer end. So rarer means actually, at lower density. అంటే ఇక్కడ థిక్ నుంచి థిన్ దగ్గర ఇది రిఫ్లెక్ట్ అవుతుంది. థిన్ మీన్స్ ఆటోమేటికల్లీ యు ఆర్ హ్యావింగ్ లెస్ డెన్సిటీ ఉన్న రీజన్ నుంచి వస్తుంది. సో అందుకే దీన్ని మనం ఏమంటాం అంటే రిఫ్లెక్షన్ ఎట్ ఫ్రీ ఎండ్ అని అంటాం, ఆర్ రిఫ్లెక్షన్ ఎట్ నాట్ ఎగ్జాక్ట్లీ ఎట్ డెన్సర్, సో దట్ ఈస్ రేరర్ ఎండ్, సో దట్ ఈస్ lighter the density. So then what happens is, let us understand the thing. Suppose if wavelength is lambda1 and wave propagation constant is k, and velocity is v1, we know that the frequency always remains as constant. In the case of reflection or transmission, already we studied that. As the medium changes from thick to thin, automatically velocity changes, and as well as wave propagation constant changes, and as well as wavelength also changes. So you need to understand that when the medium changes, automatically the velocity of the wave changes. When the velocity of the wave changes, according to our previous discussion, frequency constant v is proportional to lambda. When the velocity changes, automatically wavelength also changes. When wavelength changes, automatically the wave propagation constant also changes. So that thing you need to understand. Now we will focus on reflection at free end. At free end, what happens? Suppose I am taking a wave, so which is reflecting at free end. Suppose this is the free end. So this one I am taking as incident amplitude. This one I am taking as incident amplitude. So then I am going to draw the reflected amplitude. So this will be the reflected amplitude. This will be reflected amplitude. So as we studied earlier, so it suffers zero phase difference. As we discussed earlier, so it suffers zero phase difference. So that's why only, so if a crest is incident on it, so automatically, so we have the reflected wave also as the crest. The phase difference between these two waves, that is incident and reflected waves, is zero. And when we think of the transmitted wave, so we used to think if some part is transmitted, so it is also having same phase. So we used to call AP. So generally we have formulas for AR. So these are very important. AR equivalent to V2 minus V1 by V1 plus V2 into K. This is a formula we need to memorize. V2 minus V1 by V1 plus V2 into K. And when we think of AT, so that equivalent to 2V2 by V1 plus V2 into K. Or some people may take the approach of the wave propagation constant. So they will write it as K1 minus K2 by K1 plus K2 into K. Or this is equivalent to 2V1 by 2K1 by K1 plus K2 into K. 2K1 by K1 plus K2 into K. So this formula we can easily remember. We can easily remember by using the collision formulas. V1 equivalent to already we have in terms of M1 minus M2 by M1 plus M2 into U1 and V2 equivalent to, so that equivalent to 2M1 by M1 plus M2 into U1. When U2 is equivalent to 0, when U2 equivalent to 0, generally we have this much of relations. So from there easily we can correlate. From there we can easily correlate and compare. So this is very, very important logic. So you can see here. So instead of mass, I'm writing case. Instead of mass, I'm writing case. Instead of 2m1, I'm writing 2k1. I'm writing 2k1. Instead of m, we are taking k. Instead of m, we are taking k. And AR means this will be the V1 and AT means this will be V2. So now we will write the expressions for reflected wave and as well as transmitted wave. So I'm taking the reflected wave AR into sine. So if you understand the reflected wave, so only the direction of motion will changes. So that is sine omega t. As it is back into the same medium only, the first medium only, the wave propagation constant will be the same, sine omega t plus k1 into x. Or you can understand this, if we take the incident wave equivalent to A into sine omega t minus k1x. Because the incident wave is moving in the positive x direction, the reflected wave is moving in the negative x direction. And when we think of transmitted wave, it has an amplitude AT into sine of omega t, because the frequency remains constant when the medium changes, minus, but wavelength changes. So that's why the wave propagation constant changes. So you need to memorize this. So as it is into the second medium, so definitely the wave propagation constant changes. So that's why in the second case we are having AT equal to sine omega t minus k2x. So these two are very famous equations. These are very important. So these two are very important. So directly we will get the respective amplitudes and as well as respective waveforms. Similarly, we used to observe the reflection at residence. Reflection at residence we are taking. Suppose we will understand what is the residence. Suppose I am taking thin wire. So later on this we are taking thick wire. So this is thick wire and this is thin wire. For example, I am taking that a wave is propagating like this. A wave is propagating like this. And if it is reflected back, this is reflected lay. So we are taking, this is the reflected. If it is reflected back, at the boundary of denser medium. So at the boundary of, if the wave reflected back at the boundary of denser medium, so we will call that is the reflection at rigid end. So here generally it will use a principle called as Stokes phase reversal. Stokes phase reversal. So let us see what do you mean by Stokes phase reversal. So that means when a wave reflected at rigid end, when a wave reflected at rigid end. So whatever may be the nature of the wave, it may be sound wave or light wave or any wave reflected at rigid end, it suffers additional phase difference pi radians. It suffers additional phase difference pi radians. So that's why you can see here, whenever the crest incident on the surface, automatically we are getting from, and for the problems related questions, the story is same. So again, we will write the incident wave equivalent to A into sine. From the first medium, it was moving omega t minus k1x. So similarly, we will take the reflected wave. So we will understand from here. Suppose this is the AI, this is the incident amplitude, and this will be rigid end. This will be the rigid end. So automatically, after substituting the values or data, it found to be we are going to have negative amplitude, that is trough we are going to have. And of course, we have 80 as it is in the same case that of AI. So YR equivalent to reflected wave, we are going to get AR into sine of omega t. Reflected means again it will be back into the same medium. So therefore the wave propagation constant, but the direction changes. So instead of omega t minus k1x, so we have omega t plus kx. So when we think of transmitted wave, so yt equivalent to at into sine, we can see that in the transmitted wave, the wave travels from first medium to second medium. So at into sine omega t minus k2 into x minus k2 into x. So we need to understand this. So this is very important. So this is about reflection at free end and reflection at rigid end. Suppose we will take care of a problem. Suppose the incident wave equivalent to y equal to 2 sine of 4x minus 8 is reflected at x is equal to 0. X equal to 0 from first one is free end. And second one is fixed end. First one is free end and second one is fixed end. So we need to understand free end means rarer medium and this is denser medium. So when we think of free end, we know that only the direction will change. Suppose if this is the incident wave, automatically we have reflected wave like this. Only the direction changes. So this is the incident wave and this is the reflected wave. So for the first case, we are writing y reflected equivalent to. So we will write just 2 into sine 4x plus 8. And when we think of the second wave, second one, so when this is the denser medium, if we take the crest, automatically we are going to have trough. So that's why the amplitude will reverse, it gets reversed. yr equivalent to, instead of 2 we are having minus 2 and sine of 4x plus 8. So this minus 2 is for rough and plus sign is nothing but the direction changes. So the direction of motion will. So now we will understand the standing waves, or we used to call the stationary waves. So we will take standing waves, or we used to call them as stationary waves. We used to call them as stationary. So actually, we will understand the situation here. So that means if this is a wave, if a wave is progressing like this, if a wave is progressing like this, and if it is reflected from a rigid boundary, so automatically we are going to have the reflected wave. So the reflected wave, the reflected wave, so the reflected wave will be superposed on the incident wave. So finally we are getting standing wave. Finally we are getting standing wave. So here in the standing waves, generally we have nodes and as well as antinodes. So antinodes means these are the positions which have maximum displacement. So here we can see these are the antinodes position, and clearly this will be the node, and that this will be the node, and again this will be the node, and this will be the node, and this will be the node. So here a few important points we are going to discuss it right now. Suppose the distance between successive nodes. Successive nodes is nothing but this. So node to the next node, so that equivalent to lambda by 2. And similarly, the distance between successive antinodes. So that is also equivalent to lambda by 2. The distance between successive nodes equivalent to lambda by 2, and the distance between successive antinodes equivalent to lambda by 2. And the distance between antinode, successive antinodes and nodes. The distance between successive antinodes and nodes is equivalent to lambda by 4. So we can see this. So this will becomes lambda by 4. And the most important thing is the phase difference. The phase difference between the particles within same loop is equal to 0, is equivalent to 0. So that means in the same loop, all the particles will vibrate in same phase. So that is very, very important. So that is in the same loop, all particles vibrate in same phase. All the particles vibrate in same. And the phase difference between two adjacent loops, the phase difference between the particles, between two particles, between two particles in adjacent loops, is pi radians. And here you need to remember one thing, that here the phase difference equivalent to k into x is not valid. K into x is not valid. So this is very, very important statement. So this is valid for progressive waves. So this is valid for longitudinal waves. So this is very, very important point. Just we need to understood. So between the first loop to second loop, we have a phase difference pi. Between the first loop to the third loop, we have a phase difference 2 pi. Between the first loop to the next loop, we are having phase difference 3 pi. So in this way, we need to understand about the basic properties of stationary wave. Now, about the problems discussion we are taking. So we are taking the different approach. Suppose if incident wave equivalent to A into sine omega t minus kx. And suppose it is given that if the reflection takes place at resident, so automatically the reflected means we have a reflection minus A into, because instead of plus we are having plus minus A into sine omega t plus A. So we are taking this principle of superposition, that is incident plus reflected. So we are going to have minus 2A into sin x into cos omega t. Cos omega t. Or without understanding all these things, just by seeing its value, so directly we are able to locate the location of nodes and antinodes. So let us see. So here observe this equation, minus 2A into sin kx. Minus 2A into sin kx. So that means that this is a sinusoidal wave. So the resultant wave is a sinusoidal wave. It appears as sinusoidal wave. So therefore, starting from x is equal to 0, the wave starts, and we have a wave like this. And we have the reflected wave. So this will be the resultant wave. So whenever you get this idea, by taking minus 2A sin kx, and this will be a sine, whenever you get the idea, so there is no need to remember any formulas. So directly we will write the location of nodes and as well as antinodes. Suppose this is the node, and this is the node, and this is antinode, and this is antinode. Clearly we will write at x is equivalent to 0, and x equivalent to lambda by 2, and x equivalent to lambda. So definitely we have nodes. And clearly we will say at x is equivalent to lambda by 4. So because this much distance, this distance is lambda by 4 only, lambda by 4, and 3 lambda by 4. So we have antinodes. So that means if we have an equation like this, suppose if I am taking another example, if y equivalent to, let us say, it is in the form of 2A sin kx into sin omega t also. So when we think of the amplitude is again sine wave. So that means the wave looks to be a sinusoidal. So that is very important. And the choose separate structure. Sine form lo unte just a sine wave తీసుకుంటే సరిపోతుంది. ఇలా sine wave తీసుకొని, and you need to think of the reflected wave. Next, we will think of reflection at the free end. If the reflection is at free end, so we will write y incident wave is a sine omega t minus kx. So at free end there is no phase difference. So therefore we have a into sine omega t plus kx. So if these two waves superpose each other, y equal to yi plus yr, we get a 2a cos kx into cos sine omega t. So that means just observe the wave. So this will be a cos wave. This will be the cos wave. So that means I'm going to construct this. So if this is the incident wave, if this is the incident wave, so the incident wave should be cos. So automatically after reflection, the wave will be like this. So after reflection, the wave will be like this. So this will be the situation. So that means we will understand that. So this is antinode. So antinodes are located at x is equivalent to 0. So initial point itself we have an antinode, and we note that two antinodes are separated by a distance lambda by 2. So therefore lambda by 2 and lambda and so on. And just by seeing this, we will get nodes at x is equivalent to lambda by 4, 3 lambda by 4, and so on. So this will be node and this will be node. So the same possibility also exists for another example. I'm taking y equivalent to, so let us say 2a cos kx into cos omega t. So for this also we do the same procedure. So that is 2a cos kx into cos omega t. X is equal to 0. We have antinodes, and x is equal to lambda by 4. We have. Next, we will observe standing waves. Standing waves on a string which is fixed at both ends. Standing waves on a string which is fixed at both ends. Okay. So now we will think of standing waves on a string which is fixed at both ends. Suppose I am taking this is a string, so which is rigidly fixed at both ends. So we need to get the minimum part of the stationary wave. Suppose a wave starts like this. So this is the minimum possibility of a stationary wave. So we used to call this as fundamental frequency. Fundamental frequency. Or we used to call this is the first harmonic. Harmonic means we need to understand its meaning. So that is harmonic means this is the possibility. This is the possibility. So when we think of fundamental frequency or first harmonic, first possibility, just we will understand that. So this is the node, and this will be the node, and the length of the wire is equivalent to lambda by 2. So therefore lambda equivalent to 2L we are writing, and the frequency equivalent to V by lambda. So that equivalent to V by 2L. As this is the fundamental frequency, simply we will write as, so it is here, there's no issue. Fundamental. And as this is the first harmonic, we are writing F1. F1 equivalent to V by 2L also. And we know the velocity of the wave in stretched strings as root of t by mu. So therefore 1 by 12 into root of t by mu. We will do. So this is a very important basic here. So this is the fundamental frequency. So this is also equivalent to here, and we call this is the fundamental frequency. Fundamental frequency. So next we will think of second harmonic. Second harmonic, or we used to call it as first overtone. Second harmonic or first overtone. So now we are discussing second harmonic, means second possibility or the first overtone. So if we think of a standing wave, so the next possibility, you need to remember one beautiful thing, that from when the harmonic is increased, or when we think of the next possibility, so for the next possibility, you are going to have an additional loop. In every next possibility, whatever may be the discussion, it may be open pipes or closed pipes or whatever it may be. So in the next possibility, automatically we have some additional loop. So that is the easiest way to remember. So you are going to have some additional. So then we will say the length is nothing but lambda. So here I am taking this is called as F2. F2 equivalent to V by lambda, that equivalent to V by L. So I am writing it as, for my convenience, I am writing it as 2V by 2L. And that is equivalent to 2L. That is equivalent to 2L. So this is called as a second harmonic. Second harmonic. So now we will easily understand the relation between the harmonics and overtones. So now I am writing the possibilities, the possible frequencies, of a stationary wave in stretched string. Of a stationary wave in stretched string. So that we are taking the possibility as F. So the first possibility is F, first harmonic, second harmonic, third harmonic, fourth harmonic. So we will take and so on and so on. So you need to understand the definition of overtones. Overtone definition means the frequencies which are higher than the fundamental frequencies. So all these are called as overtones. So this is a beautiful way to understand the overtones. So overtone means the frequency higher than fundamental frequency. So as this arrives in the first place, so that's why it is called as first overtone. And as this arrives in second place, so this is called as second overtone. So in this way, without confusing, so easily we will understand the harmonics and as well as overtones. And you need to understand that. So when we think of a loop, so you need to understand that number of loops. If number of loops equivalent to n, so then that is equivalent to number of harmonics. Just now we have studied. So from this harmonic to next harmonic, so only one loop increases. number of harmonics equivalent to number of loops, and that is equivalent to number of antinodes also. So number of antinodes also. We can sense that. You can see in one loop only we have one antinode. So therefore we have n number of antinodes. So then we will see that if we have n loops, so automatically we have n plus 1. We have n plus 1 number of nodes. Number of nodes. And similarly, if we are considering nth overtone, if we are taking nth overtone for the strings, so it will be n plus 1th harmonic. N plus 1th harmonic we are taking. Okay. So we will take a simple problem of this. For example, we have support like this. We have a while. And we have another while. So we have a thick wire which is suspended vertically by means of two strings. So the first string has a tension T1 and the second string has a tension T2. That is it. And this is the A is a point of suspension of from the one string, and C is the suspension on the string. This is BD points. Suppose if you are locating at a distance x, and the total length is given as L, let us say. L, let us say. So automatically this distance will be L minus x. L minus x. So then the question is, if the frequency of left wire is twice that of right, then find the value of x. Find the value of x. So left means f. F1 equivalent to 2f2 f. We know that any frequency is directly proportional to root t. So therefore root t1 equivalent to 2 into root t2. Or t1 equivalent to we are having 4 into t. So but according to the system of particles, so the torque executed by the T1 is equivalent and opposite to the torque executed by the T2. So therefore, this is axis of rotation. So from this axis of rotation, we are taking from this axis of rotation. Torque means force into perpendicular distance. This is the force and this is the perpendicular distance. So T1 into x equivalent to the force is T2 and the perpendicular distance is L minus x. So then only the system will be in equilibrium. Under equilibrium condition, we are doing the plot. So if T1 equivalent to 4T2, so 4T2 into x is equivalent to T2 into L minus x. So T2, T2 gets cancelled. 4x is equal to L minus x, or 5x is equivalent to L, or x is equivalent to L by 5. X is equal to L by 5. So in this way, you will understand the discussion. For example, we have a string fixed at both ends. A string fixed at both ends has consecutive waves, has consecutive waves for which the distances between the distances between nodes are 16 centimeters and 18 centimeters respectively. Then find number of loops are harmonics. Then find number of loops are harmonic formed inside the string. Actually, we are taking that a string is fixed. A string is fixed at both ends. It has consecutive waves for which the distance between the nodes are 16 centimeters and 18 centimeters. So that means you are seeing nodes, successive nodes at a distance 16 centimeter and 80 centimeters. Suppose for the nth harmonic we are taking, suppose if this is having nth harmonic. So consecutive wave means first we are focusing on a wave, first wave. So for the first wave, if we have n loops, so then we will say that automatically n into lambda 1 by 2 equivalent to length we are. So and the distance between the nodes, for the first wave, the distance between the nodes, that is lambda 1 by 2 equivalent to 16. So therefore one is 16 and the other is 18. So therefore I am taking it is n into 18 equivalent to. So we are taking the next possibility. So therefore we are taking n plus 1th harmonic. N plus 1th harmonic we are taking. So that means in the same wire we are having n plus 1 loops. So n plus 1 into lambda 2 by 2 equivalent to n. So therefore n plus 1 into lambda 2 by 2 is nothing but in the case second case the length will be 16. 16 equivalent to n. అంటే మనం ఎలా చూసుకోవాలి అంటే ఎన్ని ఎక్కువ ఉంటే ఈ వాల్యూ తక్కువ ఉండాలి. ఎన్ని ఎక్కువ ఉంది కాబట్టి ఇలా మనం కంపేర్ చేస్తే 18L equivalent to 16n plus 16, or we get 2n equivalent to 16, or else we will get n equivalent to 8. So in this way we will do the problems here. Suppose a harmonic stretched string, fixed at both ends is vibrating in fifth harmonic. According to equation, so let us, it is given as y equivalent to 0.01 sine of 62.8 meter inverse into x, and cos of 628 second inverse into t. So then that will be the case. We will let y equivalent to 2a into sine kx into cos omega t. So we are taking this question. So we need to find out everything, that is number of nodes, number of antinodes, and frequency, maximum displacement, everything we will find out. So by seeing this is the stationary waveform, just I'm comparing the first one. So 2a equivalent to 0.01. And this will be the maximum displacement. Maximum displacement. So this is called as maximum displacement. And here we will see is vibrating in fifth harmonic. Fifth harmonic means the number of nodes. Number of nodes equivalent to 6. Because in the fifth harmonic we have 5 loops. 5 loops. So when we have 5 loops, the number of antinodes is equivalent to 5. Just now we have said it. Number of loops equal to number of antinodes. And the n plus 1 nodes we are having. That's why you are having 6. So when this is the case, so we are taking of this wave propagation constant initially, k equivalent to 62.8, and when we think of angular frequency omega equivalent to, so let us say this is 628. So this is 628 and this is 62.8. Omega equivalent to, so this is omega, so therefore omega equal to 628 I am writing, so that equivalent to 205. As this is the fifth harmonic, so we have 5 loops, so therefore I am writing it as 2 pi into f5. So therefore f5 equivalent to 100. As this is the fifth loop, we are having f5 is equivalent to, fifth harmonic means 5f, 5f is equivalent to 100. So therefore the fundamental frequency is going to be 20 hertz. 20 hertz. And next we are writing velocity of the wave. Velocity of the wave. So when we think of velocity of the wave, v equivalent to omega by k. Omega is 628 and k is 62.8. So therefore the velocity of wave is 10 meters per second. So in this way, we will understand about the stationary wave.